Hello, this is S&D College of Engineering and Research Center, Yeola, lecture series for first year engineering. I, Chaudhary Vivek Sitaram from first year engineering department. Today's topic is about the introduction to an optical fiber. So as we know, in an optical fiber, it is having the core, the cladding and the outer jacket. These are the three main points, and it is looking like just a hair, as thin as hair, and flexible medium. And the fiber which are used for optical communication are the waveguides. The light is guided through an optical fiber, that's why it is called as a waveguide. Its function is to guide visible and infrared light over a long distance. As we we saw before also, it is having the core, then the core is covered by the cladding, then there is a coating, and after that coating there is a strength member, and after that there is an outer jacket. So that's why, as the optical fiber is brittle and it is made up from the glass and silicon, so that's why it require large strength. So protection is needed. Now the main point, the working principle of an optical fiber. The working principle of an optical fiber is the total internal reflection. The principle of light transmission through an optical fiber is total internal reflection. The conditions are the refractive index of the core must be greater than the cladding. At the core cladding interface, the angle of incidence must be greater than the critical angle. So as we know, so when ray of light travels from the denser medium to the rarer medium, then what happens? The angle of incidence is greater than the critical angle. The ray reflects back into the same medium. That is total internal reflection. In an optical fiber, so now we see from the different diagrams. Now here is the below dark given material, that is dark blue material, is having the refractive index mu1, and the above that there is a cladding material which is faint blue for in this figure. So mu1 is always greater than the mu2, that is the refractive index of the core is always greater than the refractive index of the cladding. When light is allowed to fall on the interfere or on the boundary between two media with the angle less than critical angle, then what will happen? The light is refracted. And when light is allowed to incident from the denser medium to the rarer medium, then it is bending away from the normal. So phi r, that is refraction, angle of refraction is phi r. Now when we increase the angle of incidence in the middle one figure, so the angle of refraction becomes 90 degree, and the angle of refraction where angle of refraction is 90 degree, for that angle of incidence it is called as critical angle of incidence. Now if we again increase the angle of incidence greater than the critical angle, then the light is bending again away from the normal and it is totally internally reflected. So when we are allowing light that is having the angle greater than the critical angle, then light gets reflected into the same medium, and this is the basic principle of an optical fiber, total internal reflection. As we know, so this is having the total internal reflection. In an optical fiber, rays undergoes repeated total number of reflections until it emerges out of the other end of the fiber, even if fiber is bent. When light is incident on the core of the fiber optic, it will be refracted and will travel in the core, and after some time it will strike on the other cladding interface. Now structure of an optical fiber, it is having core, cladding and buffer coating. So core is having the width of 5 micrometer to 100 micrometer, and cladding is more than that, and the buffer is more than that. So total width of an optical fiber is 250 micrometer to 300 micrometer. So now when critical angle of incidence we had seen that, now if by using we are going to utilize Snell's law. As we know Snell's law, angle of incidence and angle of refraction. Then what will happen? Mu1 into sine of angle of incidence is equal to mu2 into sine of angle of refraction. So here the critical angle is 90 degree. Then if we put it, then sine theta, that is critical at for total internal reflection, sine of angle of incidence, that is sine of phi I, should be greater than mu2 upon mu1. Now for numerical aperture, when we observe this geometrical point of view, mathematical point of view, so theta I is the angle of incidence, theta R is the angle of refraction, and phi is that angle where it is incident on the boundary between the two media, that is core and cladding. So, okay. Now in triangle ABC, if we observe that ABC, C is having right angle triangle and theta R. So sine of theta R is equal to sine of 90 minus phi. So 90 minus phi is obviously cos of phi. So sine theta R is equal to cos of phi. So then from equation 1 and 2, sine theta I is equal to mu1 cos phi, and from this equation sine theta I maximum is equal to mu of cos phi. Now if we again go on, then by solving, then we get sine of theta I maximum is equal to mu1 under root 1 minus sine of phi c, and as we know sine of phi c for critical angle it is equal to mu2 upon mu1. If we put it, then we come to know then sine theta I is equal to under root mu1 square minus mu2 square. That is nothing but the numerical aperture is equal to square of the angle of refraction, refractive index of the core, and difference of the refractive index of the core and cladding. So now numerical aperture and acceptance angle. So numerical aperture is equal to numerical aperture is defined as the sine of the acceptance angle. So numerical aperture is equal to sine of the acceptance angle. So numerical aperture also is equal to under root square root of mu1 square minus mu2 square. It is the difference of the square of the difference and square root of it. Okay. Now acceptance cone. The light entering the core in cone of semi-vertical angle is transmitted in the core through total internal reflection. The cone is known as acceptance. It is a half angle cone. Okay. Thank you.